Okay, so I guess we can start. So good evening, everybody, and welcome to this PhD talk. As usual, I remind you to fill this table with your name and your email. So our speaker today will be Giacomo Rizzieri. Giacomo is from the ISSG program and he's enrolled in the 37th cycle. He's working under the supervision of Professors Ferrara and Cremonesi, and his topic of research is numerical modeling of 3D printing of concrete. That I guess will be the topic of today's seminar. So, just a quick reminder, as Professor Frangi told me, in 10 days we will have the Polymiran, which is also one of the first DICA Olympic Games event. So don't forget to register for this event if you participate in the DICA Olympic Games. So now, without further ado, I just leave the floor to Giacomo. So the floor is yours.
Okay, thank you, Chiara, for the introduction. So welcome everybody. Well, yes, my topic is numerical simulation of 3D concrete printing. So without waiting any much time, this is the plan of the talk, but before starting, I will just want to give you an introduction about what is 3D concrete printing, because probably not all of you knows 3D concrete printing and what are the advantages of this new technology. So, in 3D concrete printing, generally there is a robotic arm or a gantry system which is used to govern a robotic control nozzle which moves and is used to extrude a cementitious mortar in order to create objects layer after layer. So there are many advantages linked to these technologies, and I want to present them to you a little bit by showing a few projects that I like about 3D concrete printing. So let's see, the first one is the Striatus Bridge. It is a pedestrian bridge which was firstly showcased at the Venice Biennale a few years ago. So maybe some of you had the chance to see it. And I think it's interesting because it's a formative structure, so we have a complex shape in order to achieve only compression stresses inside the material. To build this structure, they use different panels of different sizes and shapes, and all these panels were 3D printed in the facilities at the ETH Zurich group. So you see that the printing, obviously this is not the printing speed, but anyway it's a very fast process, and also it allows to achieve very great accuracy. Okay. So another project, which is I would say a much larger scale project, is this 3D printed wind turbine tower developed by Cobot, and you can see that also here the advantages are the fact that we are able to create circular shapes with ease, and also the fact that we are using less material than in conventional structures, because we are able to create this infill pattern in the section. Finally, a smaller example, which is from the 3D lab of the Ghent University. I like this one just because we can have a closer look to the material, and also you can see that a shape like a dome can be printed without any formwork. So the formwork in a standard structure can constitute up to the 30% of the cost. So 3D concrete printing is able to reduce the cost because we don't need formwork to create very, let's say, also strange shapes. However, in order to exploit the potentialities that this technology can bring, we need to fully control it. And today it's still under development. We don't have regulation. We don't have a deeper knowledge about this technology. So I think 3D concrete printing numerical simulations can help from this point of view. For example, I listed here some of the reasons why. We are able, with numerical simulation, to predict the geometry that we are going to print. We can also predict whether the print will be stable or it will fail during printing. And finally, we can use numerical simulation to optimize the printing process, both from the material point of view by developing new mix designs, or also from the point of view of the process by optimizing the printing paths and so on. Okay, now coming to the numerical simulation, there are three main families of numerical simulation tools available. However, all these families are still under development, so they are not ready to use tools. We can see that the solid single-phase models, which are this one on the top left, they use the idea to activate solid finite elements along the paths to reproduce the printing. And they have the advantage that they are they allow to create, to simulate the object, but they don't reproduce accurately the flowing process. Then we have discrete element models, which particles are used to reproduce the concrete. And the problem here is that to have a very accurate simulation, we need a lot of particles, because they must be of the size of the grains in the concrete. And also, it's more difficult to formulate a constitutive law for a particle to represent the particle's interaction. So the method on which I will, the family of methods on which I will concentrate today is numerical fluid single-phase models. And so the idea here is, okay, so I will start presenting my numerical model, which is based on the fluid assumption, meaning that the fresh concrete is assumed to be as an homogeneous fluid. And in this framework, the governing equations are the Navier-Stokes equations, which accounts for the balance of mass, balance of energy, and balance of linear momentum. Additionally, we can exploit compatibility, constitutive law, and state equation. And in the end, if we rearrange this equation, we can keep only a system of 5 equations with 5 unknowns, which are the free velocity components, the pressure, and the density. So the Navier-Stokes equations are maybe written in the next slide in the arbitrary Lagrangian Eulerian description. So the reason for this is that the ALE formulation will allow to simplify the treatment of the moving boundary conditions at the nozzle. And this is something I will show later on. But for the moment, let's just recap what is the ALE formulation. So basically, we assume that at every point, we can decouple the mesh velocity from the material velocity. So in this way, we obtain a general framework which includes the Eulerian formulation and Lagrangian formulation as subcases. In particular, we have that if we take the mesh velocity equal to 0, so the nodes of the mesh will stay fixed. And this is the Eulerian formulation. You see also that we can compute the convective term. While if we assume that the mesh velocity is equal to the fluid velocity, so we are following the particles as they move with the mesh, we are in the standard Lagrangian formulation. So here I've just written the mathematical form of equations. And on the right side, you can also see the boundary and initial conditions, because we need a suitable set of boundary conditions to create a well-posed problem. Now, before going on with the discretization, I want to spend a few words about the constitutive law, which for a fluid is generally referred to as rheological law, and we are linking the deviatoric stress tensor to the deviatoric strain rate tensor. And if this law is linear, we are in the case of the Newtonian fluid, which maybe is more familiar, for example, water. While in the case of concrete, we need to use a model, for example, the Bingham fluid is the more used. And the idea here is to have a threshold in the stresses, which is called the yield point, and below the yield point, the material behaves as rigid, while if the yield point is overcome, the material will start to flow. just coming back here, you can see that the yield point represents numerically a singularity because of this sharp edge. So when we implement it in the code, we decided to use the Papanastasiou regularization, which is an exponential smoothening. And so the idea is we have this exponent m. As we increase the exponent, we are able to recover more and more the true Bingham behavior. Okay, now to conclude with the mathematical part, we need to solve the Navier-Stokes equation in numerical form. So to do this, we start by writing the weak form. Then we assume some finite element discretization with linear shape function. Also, this will be clear later on why. And we obtain the semi-discretizing space equations. Then we need also to discretize in time. And to do this, we chose to use a central difference scheme, which is second order accurate and explicit. But being explicit, we need to respect the CFL condition. And the CFL condition is a condition on the maximum allowable time step that we can use during the analysis. And it's linking this time step to the minimum characteristic element size in the mesh. So we have that the time step that we can use in the analysis is linked to the quality of our mesh. And this is very important. And this is also why we need, now that we have treated the finite element discretization, introduce a new concept, which is the particle finite element method. And basically, the idea is simply to observe that if we have a fluid, like also a viscous fluid, like in this case, the fluid will undergo large deformations. So if we assume to use a Lagrangian formulation in most of our domain, also the mesh will deform, will be distorted, and we don't want a distorted mesh, not only because we are losing in accuracy, but also because of what I told you before about the CFL condition. So every time that we have, during the analysis, a mesh which is too distorted, we are going to delete the elements and perform a remeshing scheme, which is summarized here in two steps. First, the Delaunay triangulation, and then with the alpha shape method, we recover the true domain. Okay, so now I have presented to you the, let's say, the fluid solver that we are using. Now we'll enter more into detail with how we particularize it to treat 3D concrete printing. So in 2D, we started with a bidimensional model because it's easier. And so this is the first idea introduced when I told you that we were using the ALE formulation, and now you can understand why. Because if we want to assign two boundary conditions to the same set of nodes, you can see the gamma set of nodes which are at the end of the nozzle. This set of nodes must move with the velocity of the print, which is the velocity at which the nozzle is translating. But at the same time, we need to reproduce the inflow velocity of the fluid which is coming out of the nozzle. And you need also to take into account that this printing velocity, in this case I draw it horizontally, but can also have some components which are vertically, for example, when we raise the nozzle. So to combine this boundary condition, the ALE description works very well, and this is what we used. While in the rest of the domain, omega, we are going to use a standard Lagrangian formulation. Now, having a closer look at the nozzle, we can see that the ALE nodes will transmit this boundary condition of the inflow to the Lagrangian nodes connected to it. So the Lagrangian nodes in time will start to flow down, and at a certain point these elements will be very distorted, and we will add some additional nodes in the middle to represent the continuous flow of the material. Okay, so let's see some examples of the printing process in 2 dimensions. For example, in this case, I took the parameters from this work of Reynolds in the literature. We can see the printing of 3 layers. So you can see here the velocity field, it's 0 almost everywhere except at the printing nozzle. And this reflects the fact that the material, after it has been printed, it's retaining its shape. While if we look at the pressures, we can see the pressures are increasing as the layers increase, and this is something that we expected. But also we can see that there is a local increase in the pressure, and this is due to the dynamic impact of the material flowing out of the nozzle. Okay, now, this comes what I was telling you before, the fact that we can have multiple components for the translation velocity. So in this case, if we print on a curvilinear surface, the nozzle will be translating both on the horizontal and vertical direction. And both these components are changing their intensity, their modulus in time. So this case can be easily treated with the formulation I presented to you, because we are able to simulate also printing over curvilinear paths. At this point, we started to think about the computational cost, because the formulation that we used was quite costly, because we are simulating quite long time, and also we are using a lot of degrees of freedom. So the idea was to do something like a derefinement. So we start with a refined mesh, but then where we don't need to have a refined mesh, we started to remove nodes. Yes. Okay. So you can see here that the nodes are being removed after the nozzle is going away. And this reduced drastically the computational time. This example is also the, let's say, the bridge to the 3D model, because in 3D the computational cost is increasing exponentially. So to present to you the 3D case, once again, the refinement that I show you in 2D can be generalized in 3D. And we used a geometric criterion to define which portion of the material of our domain should have a certain mesh size. But this geometric criteria is not arbitrary, it's strictly linked to the velocity field gradient. In fact, you see that where we have a strong gradient in the solution, we want to use a finer mesh, while when the gradient is low, so the solution is almost constant, we can accept a much coarser mesh. Here is another technique that we introduced to treat the contact of the layer with the ground. So you can see that in the standard particle finite elements application, generally what is done is to have a plane of nodes on which you print in which the object can fall, and then some elements that you can see also over here will form. And these elements they introduce a little bit of variation in the volume conservation. So to minimize this problem, we implemented a simple algorithm which is tracking the z coordinate of the nodes. And when the node z coordinate goes below a certain threshold, we are going to assign to the node a 0-degree boundary condition. In this way, we obtain a very smooth contact. So let's see some simulation. In this case, we have a single layer which is printed. And you can see here that we are printing from a very, from 17.5 millimeters, so quite high. And we obtain a very rounded layer, and also the contact algorithm is working fine. Then we can see what happens if we print at the H nozzle, which is smaller, 12.5 millimeters, and we obtain a more, let's say, rectangular layer. You can see the shape is really changing here. And finally, we can go to an extreme case in which we print at a few millimeters from the ground, and and we are able to simulate a layer which is very squeezed. So obviously, well, maybe I can show you also just this slide, which we have a comparison of the top view profile of the layers. So you can see from the top the difference in the different layers. So if we want to print something, we can use the 8th parameter to adjust the width of our segment. But we need also to keep in mind that to obtain different layer shapes, we need to have different pressures in the material while we print. And you can see it here, the bottom view. When we print the layer which is very squeezed, we are going to have very high pressures. And this is something that designers should take into account when designing 3D concrete printing. Okay, we did some validation of the model by comparing with the experimental results. We obtained quite a good agreement in terms of cross-sectional shapes. And the experimental data is taken from the literature, and our model is also compared to other numerical models in these figures. Okay, now I will introduce one final concept regarding what happens if we want to print multiple layers on top of each other. And in this case, we need to take into account the fact that the layers have contact between them. So the contact algorithm here is a little bit more complex, but the basic idea is, first of all, we want to have an interface which is straight. And you can see that in this case, the interface is not straight because of this red element which is forming over here. So to avoid that when we when we create the mesh, these elements are generated, we perform the two operations. We refined the free surface of the upper layer, and we removed some of the nodes which are too close to the lower layer free surface. In this way, we are sure that the interface will remain straight. Once the interface is straight, we can delete all the elements forming between the two layers. So this green element here is deleted, it's not present. But what we do is we keep track of the volume of this fictitious element, and as these elements decreases in volume, at a certain point the volume will be very low. This means that the two layers are very near each other, and what we do is we remove one of the nodes of the elements, and in this way we obtain an updated contact configuration. Obviously this process is iterated a lot of times to simulate the continuous print of the upper layer on top of the other one. So let's see some results. For example, here we have the print of 3 layers, one on top of the other. It's just a single filament, but it's folding on itself. And you can see how the contact algorithm is works very smoothly, because you see, as soon as it goes here, okay, you see over here it's very clean. So we have a minimum volume variations in this case. Okay. Also for this case, we were able to validate the results with some data in the literature, and we obtained a very good agreement also in this case. Okay, now I will jump back to the 2D just for a few slides to let you see how we can improve our constitutive law, our logical law. And the idea is that since when we print, as soon as the material reaches the ground, it will start in time to consolidate. So what I mean with consolidate, firstly the particles will flocculate together in a reversible process, and then with time, because of the hydration reaction, some products of hydration will start to create bonds, and the material, as a result, will increase its mechanical properties in time. To take this into account in the model, we used this thixotropy model from Kruger, which is a bilinear model, and it's assuming that the yield stress, which is a very important parameter as we saw earlier for the material, so this yield stress is increasing in time with this law. So we inputted this model in the hours, and to show you how it works, I present you this example, which is more or less taken from this paper of Kruger. So we are printing a layer, and then after the layer has been printed, we wait some time, and then we print a second layer, then we wait some more time, and so on. In this way, we are going to see very well the effect of thixotropy. So first of all, let's see what happens when we print just one layer. We can see that the yield stress is increasing along the entire layer. Then when we look at the entire object, the printing process looks like this. You can see that every time we print a layer, we also update the time, increase the time, so the yield stress as a consequence will be increasing. And we have a material which has different mechanical properties on each layer. So then, in order to assess what is the impact of thixotropy or structuration of the material on our object, we decided to do the same simulation, also without the evolution of the mechanical properties. You can see here the comparison. So the red curve represents the simulation without the evolution of the mechanical properties, so no thixotropy. And you can see that if we have no thixotropy, the object starts to deform a lot more, and there is also some problems during the print, these localized depressions over here. So we conclude that in general, thixotropy is good for 3D printing, and maybe this 2D model is not enough to assess accurately the thixotropy, but with a three-dimensional model, we would be able to really quantify how thixotropy is entering in the printing process. Okay. So now I will show you some examples of more complex printing processes. And so, first of all, let's recap what is the design process for a 3D concrete printed object. So we start by a 3D CAD model of the object. Then we slice the model in order to obtain all these slices. Then there is a software which generates the tool paths. So a continuous path which spans all the slices. And finally, this continuous path is discretized and translated into the G code. So the G code is basically a set of a code, a language, which contains a set of instructions which tell the 3D printer robot how to move and how to extrude the material. And so the idea is that our numerical code can also take in input this G code in order to perform the simulation. So here we reproduce the case for which I showed you the G code just before, the toolpaths. The material parameters are reported below, and they are, let's say, standard generic ones. Then another example, which I think is interesting because it shows us something which can happen during 3D concrete printing, which is instability. So if we are printing too fast, or the mechanical properties are developing too slow, for example, because the thixotropy is too low, what can happen is that our object can fail during printing because of buckling, what is called generally buckling in 3D concrete printing, let's say, vocabulary. And obviously, we want to prevent this phenomenon. And we also want to see here if our numerical model is able to capture it or not. So to establish this, I perform this simulation. This is a rectilinear wall, and you can see here on the right side the cross-section. So it's printing the first layer, the second layer, and also the cross-section is updating. When we reach the fifth layer, the print collapses. And this is an example, a small example of buckling. And so we are happy because we have seen that our numerical model is intrinsically able to capture this phenomenon. And the reason is that we chose an explicit time integration. So the nonlinearities which are usually associated to the buckling phenomenon are not causing any problem for this type of model. Okay, to conclude, just one final example, which is a little bit more elaborated. It's only one layer, but it's folding on itself on the plane, and it has also bigger dimensions. The material properties are always the same on the previous two examples. So and you understand now that if we have a complex example, we need the G code to be integrated in an automatic way with our numerical code, because you cannot think of input all the points by hand. So these are the results. Here we have the top view of the print. Then I also, there are two smaller views. I don't know if you can see them. On the top, there is something related to contact. So in this case, contact algorithm is not really between two different layers, but between two different portions. The red, maybe I can show it. Okay, you can see that there are two portions, a blue one and a red one over here. And then on the bottom we have the standard contact with the ground, and you see that the green portions are representing the nodes which have become fixed because the z coordinate has gone below certain tolerance. Sorry. Okay. So heading toward the conclusions. We are planning, let's say, to introduce some improvements to the material behavior. To do this, firstly, we want to introduce elasticity. So when we are below the yield stress in our material, can we, instead of use a rigid model, use an elastic model? So this is the first thing. Then, if we want to print the longer printing times, we need to take into account the fluid to solid phase transition. This is also another problem that we need to cope with. From the printing behavior, the main problem, so first of all, we'd like to link our numerical tool with open source slicing software, for example, Cura. And then the main problem which remains is the numerical cost. So we need strategies to decrease the computational cost. This is probably the most difficult aspect. And just to give you a very, very general idea, this is my last slide, of what we are currently doing is to use, instead of a single mesh, that is what we did in all the examples I presented to you today, to use different meshes, so multiple meshes on each layer, and maybe to use, we could also think to use different meshes on different portions which are not on the layers. In this way, we are going, first of all, to have the possibility to perform remeshing only on some regions, not on the entire mesh. Then we are going to increase the computational power because this could allow us to parallelize more the code. Also, the meshing portion could be parallelized. And finally, probably the most important thing, we would like to introduce domain decomposition. So the idea that on different meshes we can use different CFL conditions, so different time steps and integrating time in different time steps, so increasing the computational power. And with this, I've concluded. I want to thank my supervisor, Prof. Liberato Ferrara and Massimiliano Cremonesi, which are supporting my work and also working with me to develop it. Thank you.